So now we're going to take a look at an example, and that example is going to be Ethernet, which is a standard way of doing wired networking. So Ethernet uses differential serial communication, just like we talked about. And in fact, if you take apart an Ethernet wire, you'll see these pairs of wires in it. Each one of those pairs that's twisted together is exactly the plus and minus versions of the signals that get sent. It's a shared medium. What that means is that, like a bus, we have a whole bunch of devices that are sitting on the same wires and connected together. And what Ethernet does, it divides its data into packets. Unlike the serial communications we were looking at before, which just send a long stream of serial data, Ethernet data is chopped up into packets, and each packet is sent separately. So let's take a look at how this works. We have device 1 that wants to send data, and it wants to send data to device number 3. So we make a packet which has the destination, in this case 3, and the data we want to send. First, we put the destination out over the serial communications link, over the Ethernet. Device 3 receives the destination and discovers that this is a packet for it, so it gets ready to receive it. Then we go ahead and we send the data over the link. Now device 3 receives the data. Now we've sent the data, but there's a real question here. How does device 3 know the data wasn't corrupted? How do we know there wasn't something that went on in the middle which messed up the data that we got? This is a really long wire, and we need to make sure their data is correct. So what we do is we use a CRC, or a cyclic redundancy checksum. This is a code which we calculate based on the data, and if we calculate the code and we verify the code at the other end, then we can see if we received the data we were supposed to receive. So device 1 goes ahead and transmits the CRC, device 3 gets the CRC, and it calculates its own CRC. If the CRC that it calculates on the data matches the CRC that device 1 sent, then we know the data matches. And we can say that we've verified the data. If they don't match, then we know that something got corrupted and we don't accept the data, and we can tell the device to resend the data. So here's what an Ethernet packet looks like. You can see we have a 64-bit preamble. That preamble is designed to make sure that other people see that you're using the device, the wire. Then we have the destination address and the source address. We have a body, that's the data we're going to send. And then we have 32 bits of CRC, and that's the CRC that we use to verify that the rest of the message was correct. So in Ethernet, we're sharing this wire. So what happens if we have collisions? What happens if two devices try to transmit at the same time? It's a shared wire, so they're going to mess up each other's data. So here we have device 1 transmitting and device 3 transmitting at the same time. So the first thing we do is we detect the collision. And to detect the collision, we read the wires while we're transmitting them. If another device is transmitting at the same time, we're going to read back different data than what we think we're sending, and we'll see that it's corrupted. When we do detect a collision, we keep sending data for a while, for a long time in fact. We keep sending data to make sure that everybody else also sees that there's a collision. So by keeping sending data, we make sure that device 3 here also detects the collision. Then we wait. We wait for a random amount of time, and we wait for an increasing amount of time. So if we have another collision, we're going to wait even longer. This is called an exponential backoff. And what it means is that it reduces the chance that we're going to have another collision right away. So in this case, device 1 decided to wait 15 microseconds, and device 3 decided to wait 3. So device 3 goes ahead and starts, and it's able to send its data. And then device 1, which is waiting longer, goes ahead and starts and is able to send its data. So this approach of detecting collisions by reading back what we're writing and seeing if it's the same, continuing to send data so that we make sure other devices know there's been a collision, and then having an exponential backoff where we wait to see if we can send data later, works really well. In fact, it works so well that Ethernet has beaten out every other kind of networking technology. So, to summarize our discussion of I/O, there are lots of I/O devices today. The speeds are constantly increasing. As we've seen, some of them have lower latency and higher cost, or higher capacity and lower latency. There are trade-offs between cost and performance for I/O devices. Parallel buses outside of chips are being replaced with serial links. And the reason for this is it's hard to keep long wires synchronized. Serial links are more complicated because we have to figure out where the clock is, but we have lots of extra transistors so we can do that. It's much easier to make complicated serial links than it is to make really good wires. I/O devices are mapped to memory addresses. So we've seen how we can use regular read and write commands to access them, and how the hardware looks to see if it finds the address for the device and then knows to access the device. To reduce the overhead of I/O, we talked about using direct memory access. This gives us special hardware that takes care of the data transfer so the processor doesn't have to. And we talked about using interrupts so that we only get alerted in the processor when the I/O transfer is done. And the example I gave you of Ethernet works so well that there really aren't any other networking standards. And so that approach, you should understand and remember it because that's a really, really good design.